In Chapter 12, you're going to be working with series and sequences. For today, I want you to be able to find the nth term of a sequence and write rules for sequences. So let's talk about what a sequence is first. It is an ordered set of numbers, and the term of the sequence is each number in the sequence. An infinite sequence is a sequence that contains or continues without end. And then a finite sequence is a sequence that has a limited number of terms. And we're going to be dealing with a lot of finite sequences. Sequences do not use function notation. So function notation would be a of n or f of x. They're written using subscripts. So it's going to be a little bit different notation than what you're used to. So this a sub n is used for sequences. The first term of a sequence is denoted as a sub 1. The second is a sub 2, and so on. Now, a sequence can be thought of as a function. When you're reading sequence notation, it's important to realize that this is read as a sub n. So looking at this table here, the term number is the domain. The term value is the range. So again, you can think of that as a function, that you have a domain and a range. So looking at the table above, if we want to know the value of a sub 3, we go to, would be, the n was replaced with 3, so we go to where we see an n that is equal to 3, and then we just look at the term value. That's 2. If we want a sub 5, that means find the fifth term in the sequence, and that would be just 5. So basically it's giving you a location for the term number. Really important to understand that n is the term number, not a value in the sequence. So it's very important to understand that n represents the term number. It's the location of the term in the sequence. You're also going to see a lot of a sub n minus 1 that represents the previous term, or the term that comes before the term that you're looking at. A sub n plus 1 represents the next term. If you're asked to find a sub n plus 5 when n is 4, you just push this n right in here, or place that n right there, and you're asked to find the ninth term in the sequence. So again, this is the term, the location of the term in the sequence. So that would be, again, putting the 4 in there, you'd want to find the ninth term. Okay, now let's talk about a recursive formula. A recursive formula is a rule in which one or more previous terms are used to generate the next term. So we're going to look at, try to find the next 5 terms in the sequence. Okay, now it's recursive. We're given the first term value, which is a sub 1. It's negative 2. And we want to use this rule. And this notation just means for n greater than or equal to 2. Well, why are we saying that? We're given the first term, so we want to find the second term and the other term. So the first thing that we have a sub 1. The first term, this means the first term, that's given, and it's negative 2. We want to generate the second, third, fourth, and fifth. Okay, so if we want to generate the second one, that means when I go to this rule, I'm going to write down 3, and then a sub n minus 1 for this one. Well, n is 2 for this one, so we do 2 minus 1. So we're actually looking at a sub 1. Well, what's the value of a sub 1 in our sequence? A sub 1 is negative 2. So instead of writing a sub n minus 1, I'm going to write negative 2 in there. And then I write the rest of the rule, so plus 2. Well, that's going to give me 3 times negative 2 plus 2, which is going to be negative 4. Okay, now I want to generate the third term. When I generate the third term, I write this 3 down. And n is, remember, the term number. My term number is 3 here. So it would be 3 minus 1. So I'm actually looking for a sub 2, which is the second term in my sequence. Well, that ended up being negative 4. I'll just circle these here so they pop out a little better. Okay, so we'll substitute in negative 4 here. I continue on with the rule, plus 2. I get negative 12 plus 2, which is negative 10. So a sub 3 is negative 10. That's the value of the third term. All right, now we keep going. We want a sub 4. So again, I write the rule until I get to a sub n minus 1. N here is 4. So I put a 4 in here, and I want a sub 4 minus 1. So I actually want a sub 3, or the third term, which is the previous term. So I'm going to substitute in here for a sub n minus 1, which is the previous term, negative 10 plus 2. That's going to give me negative 30 plus 2, or negative 28. So that's my fourth term. And then going to the fifth term, again, you write the rule. Then you get here where it says a sub n minus 1. We substitute, since this is a sub 5, we put a 5 in here. We want a sub 4, or the previous term value, which is negative 28. So we're going to substitute that negative 28 in here. We're going to add 2. And when we multiply 3 times negative 28, add 2, that's going to give us a negative 82. Okay, so there are terms in the sequence, and we generated this term by getting the previous term. Each one of the terms were generated by the previous term, except for the one that we were started with. We had to, when it's recursive, we need to be given one. Okay, now some sequences do not require the previous term to generate the next term. And these are called, they use an explicit formula, and it defines the nth term of a sequence as a function of n. So you don't have to get the previous term. So we want to find the first 5 terms of the sequence for a sub n equals 3 to the n minus 1. Okay, so we have our term number is n. Remember, the term number always represents n. So if we need to find n here, well, our term number is 1, so we would say 3 to the first power minus 1, and that's going to give us 2. All right, now this is not recursive, which keeps recurring or going back to the previous term, because this is in the exponent. So, these are not together, so it's not the n minus 1 like we had here in the subscript. So it's actually part of the rule. So a sub 2, we're going to go 3 squared minus 1. So that'll be 9 minus 1, which is 8. And again, we're not going back to the previous term because this one uses an explicit formula, not recursive. Recursive kind of thing is recurring again. You keep going back. Okay, now we want a sub 3, so we're going to plug in 3 for the n minus 1. So that's going to give us 27. 3 cubed is 27 minus 1 is 26. And then a sub 4, we're going to raise 3 to the 4th power, which is going to give us 81. And again, we need to go back to the rest of the rule, minus 1, which is going to give us 80. And then a sub 5, so it's going to be 3 to the 5th, minus 1, and that's going to give us, that'd be 243, subtract 1 is going to be 242. So there are first 5 terms of that sequence. Okay, now you're going to be writing some rules for sequences and series, and you need to first figure out if the sequence represents linear, linear, quadratic, or exponential. Now there's an extra one on here, square root, which we're not going to be dealing with in this section. So first we want to see if the sequence is linear, quadratic, or exponential. Now, hopefully you remember from earlier in the year that a function is linear if it has a constant first difference. So underline that constant first difference. It's quadratic if it has a constant second difference. So, now, exponential functions, you can tell if it's an exponential function if there's a constant ratio between the values in the sequence. So when I say ratio, I mean you're going to divide. All right, let's try a couple of examples. So the first thing we need to decide is it linear, quadratic, or exponential. So we're going to subtract from right to left, which is opposite of what you read. And I want you to do it that way so you get your signs correct. So we're going to do 11.5 minus 9, which would give us a 2.5. 9 minus 6.5, which again is 2.5. 6.5 minus 4, again 2.5, and 4 minus 1.5 is 2.5. Okay, so because we have a constant first difference, we know that it's linear. If these numbers were not constant the first time, then we'd have to check for quadratic and maybe even exponential. Okay, so the easiest way to do this is to, when it's linear, you write the first term. So our first term, identify that, and it is 1.5. Then you identify the constant difference, and that is 2.5. So this is the constant difference. Okay. And then you write the first term, and let's just write the template down here. So the first term plus, I'm just going to abbreviate, constants difference times n minus 1. Okay, so let's use this. We'll bring that up here. Our first term is 1.5. We're going to add that to the constant difference, which is 2.5, multiplied by n minus 1. Okay, so that's when we simplify this, we have 1.5 plus 2.5n minus 2.5. Okay, let's combine our constants. So that's going to give us 2.5n minus 1. All right, a very good idea to test your rule. And I'm going to test it. You can just pick a couple. I'm going to test it with a second term. So I'm going to try a sub 2. Let's do a sub 2. Okay, so we're right, the n equals 2. That's my term number. Whenever you see an n, that represents term number. So this is going to equal 2.5 times 2 minus 1. Okay, well, what does that equal? That's 2 times 2.5 is 5 minus 1. And my second term, and that gives me 4. And my second term is 4. Now let's check it with the 1, 2, 3, fourth term. Okay, so we want a sub 4. So it's going to be 2.5. N is 4 now, minus 1, and then we need to check and see if that equals 9. So 2.5 times 4 is going to give us 10, minus 1, and that does equal 9. So those both check. So it's pretty good indication that you have a good rule there. So a sub n equals. All right, now let's try another one here. I think you need to change this to 80 on your notes. I think you have 10 and it should be 80. Okay, well, you can probably tell by looking at it, the constant first difference doesn't work. And you might even see a pattern here that if I take this and divide that, 80 divided by 40 is going to give me 2. 40 divided by 20 is going to give me 2. 20 divided by 10 is going to give me 2. And 10 divided by 5 is going to give me 2. If that's the case, we divided. So we have a exponential function. We have a constant ratio. Ratio means to divide. So a lot of times when you have exponential, so this one's going to be exponential. Now, a lot of times you have to adjust based on what it is, but usually the basic ones, a lot of times the basics one, if you look at this, this is our base here. We know if we raise 2 to the first power, we can't get that 5. So a lot of times what you have to do for exponential is you have to take your base. Well, let's write it this way. You take your first term and you multiply it by your ratio to the n minus 1. And let me show you why that works. If we take our first term, it's 5. Let me write it over here a little bit. First term is 5, and we multiply it by 2 to the n minus 1. Well, if our first term, if we want to find the first term, when we put a 1 here, this changes to a 0, which will take whatever is in here. Anything to the 0 power is just 1. So basically, we get our first term. So let's try writing a sub n equals 5, 2 to the n minus 1. And sometimes you'll have to adjust this, but let's just try it with, we saw that it worked with our first term. Let's try the second term and maybe the fourth term. So we're just testing this out here. So a sub 2 is going to equal 5 times 2 to the 2 minus 1, and that's just going to be 1, so it'll be 2 times, or 5 times 2. So a sub 2 is going to equal 10, and that's our second term. So 1, 2, 3, let's try the fourth term. A sub 4 equals 5 times 2 to the 4 minus 1. And that's going to give us, well, that's going to give us 3 here. So 2 cubed is 8 times 5. A sub 4, so 8 times 5 equals 40. And it worked out there. Always a good idea to test your rule and make sure you can get a couple of the numbers in the sequence. And don't just test it with one number, because sometimes it works for one and it may not work for the other one. So always test. Okay, you have a couple, you try it.